Thank you for the introduction. Good afternoon, everyone. I'm Asawari Choudhari, PhD student from University of Guyane in France. Today, I would like to share with you the work done with low wave acoustic sensor and its response in highly turbid liquid environment. The motivation for this work comes from the highly turbid waters of Amazonian rivers and River Garonne in Bordeaux of Aquitaine region in France. For this, under the launch of call Innovations in French Guyana, project Sensors for Remote Sensing was selected, and it's led by SSDF Laboratory in collaboration with IMS Laboratory at University of Bordeaux. Together, the goal is development of biochemical sensor systems for environmental monitoring, especially in Greater Amazonian region. So the main objective is to test the feasibility of low wave sensors for in situ detection of target biochemical molecules such as cyanobacterial toxins, which are harmful to human health and are prevalent in the highly turbid waters of Amazonian River, where the turbidity is as high as 600 FTU, and in Aquitaine rivers, where the highest recorded turbidity is around 1000 FTU. FTU is a formation turbidity unit. The reason being, turbid liquids have cloudy and hazy appearance due to the large amount of organic and inorganic suspended and dissolved particles. And in some situations, detection of unambiguous target molecules are important to test the quality of water. Current classical methods based on optical sensors such as spectrophotometer show limitations, which could be overcome with low wave sensing method. How it could be done? Turbid liquids are also identified as complex liquids because of the presence of large organic and inorganic particles. They possess electrical and mechanical properties. And by measurement of multiphysical response of the low wave sensor, it is possible to estimate both electrical and mechanical properties of turbid liquid. So this is a low wave sensor schematic. It consists of vertical quartz substrate, SiO2 wiring layer, and titanium gold IDs at input and output. It works on the principle of piezoelectric effect. Low wave sensors are known to work efficiently in liquid media due to the high sensitivity they present because of the sheer horizontal polarization of the waves, as the transmission of the waves into the liquid is minimized. And with addition of thin guiding layer of SiO2, a few micrometers, low wave sensor presents stronger entrapment of the acoustic energy near the medium of detection. Due to the confinement of this energy, sensors are highly sensitive to the perturbations, surface perturbations, which could be detected at the output IDT in terms of shift in resonance frequency, phase, and insertion loss. This is the low wave sensor device used in our study. It is fabricated at IMS Laboratory, and it is designed at IMS Laboratory and fabricated at last CNRS facility in Toulouse. It consists of 80 quartz substrate, SiO2 wiring layer, split electrode IDTs, and has a resonance frequency of around 114 megahertz. In this study, formation-based solutions are used as turbid liquids because they are commonly used reference suspension for all turbidity measurement methods, and also they are fairly easy to prepare several concentrations which mimic the turbid solutions. To prepare formation solution, hydrazine sulfate, hexamethyl tetramine is used as per the protocol mentioned in this article, which gives 4000 FTU mother formation solution and similar concentrations of daughter solution. This is the experimental setup in clean room at IMS Laboratory. It consists of low wave sensor SLSLP elaborated in this image below. Then measure its response DNA is used, and the S parameter can also be recorded in the computer interface. These are the solution samples of several concentrations, which are localized on the sensor surface by broadcasting method using microwave. To localize the solution or liquid on the sensor surface, two types of PDMS chips are used, short chamber and a long chamber. Short chamber PDMS chip allows to have liquid only on the acoustic part, whereas with long chamber, liquid is present on acoustic part as well as on the IDT. The measurement protocol is fairly simple. Turbid samples are broadcasted on the sensor surface using short chamber and long chamber PDMS chip. Then measurement of X parameters are done with network analyzer, after which cleaning and drying step is carried out to avoid the contamination of the sensor surface. Measurements with short chamber PDMS chip allows to estimate the influence of turbid liquids only on the acoustic part by measurement of electroacoustic response and resonance frequency, which is mainly dependent on the mechanical properties of the liquid, such as viscosity and density. Whereas with long chamber PDMS chip, you can estimate the influence of the turbid liquid on both acoustic part as well as on the IDDs by measuring electroacoustic wave at resonance frequency and measurement of IO coupling, input-output coupling, and reflection loss of the input by interrogating the sensor at frequencies much lower than the resonance frequency. And it's demonstrated in this article by our team. In order to compare the effectiveness of the wave sensing in turbid liquids, optical measurements of turbid solutions were carried out with spectrophotometer. This works on a principle of turbidimetry, where a beam of ordinary white light is passed through certain path length of the sample, and the photodetectors kept at 90 degrees with the direction of travel of light detect the amount of light diverted, from which response in terms of optical transmission and absorption was measured, which could be linked to the turbidity of the liquid. All the measurements were carried out at 2 different wavelengths. In results, this is the level sensor response with short chamber PDMS chip. It's a classical method. And in the frequency domain S1 response into that, you can see the blue curve is the response due to the air. That is, no liquid present on the sensor surface. Compared to that, for DI water and all other turbid samples, the response S21 magnitude does not change much. Also, it can be seen in the S11 response that due to the absence of liquid on the IDDs, S11 magnitude does not change significantly, which means irrespective of the turbidity of the liquid, level sensors present stable response. And this allows to interpret shift in resonance frequency, phase, and insertion loss even for high turbidity liquids. And this response is usable for biochemical target detection. For sensor response with long chamber PDMS chip and alternating method, we can see in S2 response that as compared to response for air, for DI water and all other turbid samples, S2 response changes considerably. Signal to noise ratio decreases, and the impulse which we see is mainly due to the input-output electrical coupling due to the dielectric properties of turbidity. In S11 response, we can clearly see that as the turbidity of the liquid is increasing, S11 magnitude decreases considerably. And by using enriched protocol response, as demonstrated in this article, it is possible to estimate electrical and mechanical parameters of the turbid liquid by interpreting the sensor at a frequencies lower than the resonance frequency. This is the time domain response of the sensor, and due to this difference in speed of the waves, it is possible to distinguish input of electrical coupling and electroacoustic response in the time domain response. And by performing time-getting filtering of the electroacoustic energy with a further FFT, we can see that with increasing turbidity, electroacoustic energy decreases, but still it remains usable for biochemical detection with a insertion loss less than -50 dB at resonance frequency. So, level sensor can be used with both short chamber PDMS without time gating and long chamber PDMS with time gating for biochemical sensing as well as multi-parameter analysis. Whereas with spectrophotometer response, from the graph we can see that absorption is proportional and transmission is inversely proportional to the turbidity of formulated solution. Yeah. And we can see for turbid liquids with greater than 200 FTU, transmission is less than 20%. General comparison shows that with increasing turbidity, spectrophotometer response decreases, whereas lower sensor response remains stable. So to summarize, with pharmacy solutions as turbid liquids, optical sensor response degrades with increasing turbidity, high optical absorption for more turbidity is more than 200 FTU, and they have a lot of disbenefits despite their advantages such as high sensitivity, beam unit, etc. Whereas with lower sensors, we have stable response irrespective of the turbidity of the level liquids, and we can perform biochemical detection with this response. And with long chamber PDMS chip, rich set of information is available for multi-parameter analysis. So level sensor gives a reliable method for biochemical sensing as well as multi-parameter analysis with a really high turbidity values. In the perspectives, we plan to carry out several experiments with different sensor interrogation strategies to estimate electromechanical properties of the liquid, then biochemical detection using sensor and a sensitive layer specific to the target. And the work that we now opens up a possibility to design multi-parameter probe unit to estimate turbidity, total dissolved solids, and perhaps total suspended solids. With this, I conclude my presentation. I thank you all for your attention.